What I want to do today is go through a project that has consumed my life for the past 2 years and for the next 1 year, where I want to showcase how human factors in ergonomics researchers work with other researchers from other disciplines in envisioning a future for emergency response. So thank you again for the invitation. I really appreciate it. My lab is a neuroergonomics lab, and we understand, assess, and augment the human technology partnerships across various application spaces, and we have a particular focus for high-risk environments like emergency response or offshore oil and gas work. To do that, we take a mind-motor-machine interaction approach where we look at the interplay between mind and motor functions and how a human, both neck up and neck down, interact in response to the environment or the technology, and how technology in turn can change this mind-motor interactions. In our lab, we do a lot of basic research to applied work. The way I present my work is sort of in a use-inspired way. So if you understand, I recently learned about the pastures quadrant that talks about doing fundamental discovery within an application space for consideration of use. So in our lab, we do basic research looking at the neuromuscular mechanisms of fatigue. We use that information to sort of understand, what's happening in the brain, what's happening to neural drive as it sends signals to the muscles, and then use that information in a sort of superficial way to look at fieldable systems that can provide us with similar outcomes. And that can then be used for predicting fatigue in applied work settings. We have looked at the impact of fatigue and stress on human-robot interactions, looking at trust, how trust gets modulated by these operator states. We have started looking into sensory stimulation using augmented reality and virtual reality environments, and trying to understand, the application of these mixed reality tools in augmenting humans, both during training, but also during operational, work. And finally, we have started looking into the application of brain stimulation as a way to enhance worker readiness during emergency response. So today I'm going to provide you with a vision for future of work in emergency response. I'm going to talk about the motivation for why we wanted to look into this, and give you an understanding of what we mean by work, which is work as currently done. I want to provide a vision for how it might look, which is work as desired. And I want to provide examples of human augmentation technologies that can be used to amplify productivity, as well as to enhance safety, as well as career longevity. And finally, what I want to go with is how easy or how challenging it is to embed these human augmentation technologies or hacks in emergency response work. So what were the challenges that we encountered? What sort of research needed to be done? So this presentation is largely going to be my experience doing convergence and interdisciplinary research. So let me give you some premise for why we started with this. So in 2013, April 17th, there was a massive explosion that obliterated the West Fertilizer Company site in rural Texas. And it injured and killed nearly 300 people and destroyed more than 150 buildings. A multidisciplinary team of emergency responders were deployed to the scene that included more than 200 emergency medical service providers, EMS providers, firefighters, and law enforcement officers. And these were deployed at different disaster locations. For over the next 5 hours during this disaster response, the EMS providers on the scene were required or had to identify injured victims. They had to rapidly assess the severity of injuries depending, and then to decide on the next course of action. And once they decide the next course of action, which is triaging these victims, they had to lift and carry and physically manipulate moving these patients while also lifting, around 60 pounds of their life-saving equipment that they had to carry as part of their PPE. The firefighters were fighting fires in the industrial complex with dangerous chemicals. So they needed to have the situation awareness. They needed to know, what they were working with. Police officers and emergency management professionals were making quick decisions to prioritize, where resources needed to be allocated, coordinating with the teams on the disaster site that was scattered, throughout the disaster location in multiple areas that could be visibly seen or not. This is what I define as work in the domain that we are looking at. It's a collective experience of both physical and mental activities that translate to outcomes that are hopefully intended to benefit, the worker, the team, the organization, but also the community. So here, work as done was something that these emergency responders had to do in order to triage, in order to coordinate, in order to lift patients, move them to safety, but also keep themselves safe and their team safe and informed. So that is what I mean by work. Now, a bigger problem over here is also that these responders, we only have so many responders in the US, right? Like around 2.5 million responders. About 50% of the injuries in emergency responders is due to fatigue. The injury rates are 4 times that of the average injury rates for all US workers. So they are an occupation that are, significantly or disproportionately impacted by injuries. This not only results in lost time and cost, but the bigger challenge that emergency responders have told us is that, people do not want to join the workforce. This is a nuanced challenge in that if in a private industry we have shortage of workers, there could be, recruitment strategies that could be utilized, pay increase, things like that we could attract talent. However, in an emergency response, motivation to join the force and the feeling of the identity that you are serving the public is what motivates these people to join emergency response workforce. And what we find is there is a significant increase in the projected shortage in the ER workforce. So over time, we will not even have enough emergency responders. Just recently, I think in the past week, during the 60 Minutes, this is a show in the US, the 60 Minutes show, fire chief in California was interviewed. And what he said was, not only are we short on all the equipment that we need to fight these raging wildfires, we do not have enough firefighters. Even if people come from different counties to help, we just don't have enough of them to move on. So this is a big challenge for us. Now you can imagine in a future where you equip these most vulnerable working population with human augmentation technologies or HATs. You can have powered exoskeletons that could augment these workers' physical capacity, give them machine-like power to improve endurance, while still preserving their decision-making and their autonomy during disasters. And such decisions could be aided with tools like augmented reality interfaces that could help with wayfinding, that could help with situation awareness, improving situation awareness, and facilitating better team collaboration and coordination through real-time scene annotation. And these kind of augmentation technologies can transform the future of ER work. We are not there yet. We don't even have these powered exos for very structured environments in manufacturing. But we can always envision what that might look like. We also have lower fidelity passive exoskeletons that have been integrated well in manufacturing, and we can see the usage of that in emergency response. These augmentation technologies can lower responder injury rates. They can improve response efficiency by requiring fewer number of, let's say, firefighters or EMS providers to do lifting. We were told by one of a chief of the Texas emergency services that lifting a patient, an unresponsive or non-responsive patient in a confined space requires about 7 firefighters. And if with exoskeleton, we can reduce that to 2, that would be significant in working with the constrained resources in this domain. And we also feel that using these human augmentation technologies sort of provides a commitment, and folks can see, who are interested in joining the emergency response workforce, they can see that we have tools and technologies that can safeguard our health, that can improve, the sort of performance that we can provide in the field. So hopefully these human augmentation technologies can also help attract and retain ER workforce. However, a bigger challenge with this is that even existing hats, like let's say drones, right, that have been well integrated in disaster response, they are not as integrated in all of the emergency response work domains. And I think the biggest challenge over here is that there is lack of training systems that are available for these emergency responders to train on these systems, that require newer skills development, that require them to think of how work processes during an actual emergency may change based on if they use this new human augmentation technology or not. And I think that's where our biggest barrier is. So given this context, we proposed a project to NSF Convergence Accelerator that is focused on developing learning environments with augmentation and robotics for next-gen emergency responders. It took me about 5 days to come up with this title. No, I'm just kidding. But Learner is essentially a project that is very multidisciplinary, and we were the first cohort by the NSF Convergence Accelerator to get funded on this project. And I quote NSF over here in that national scale societal challenges cannot be solved in a single discipline. Instead, these challenges require convergence to merge ideas, approaches, and technologies from a wide range of diverse sectors, disciplines, and experts. So this is what NSF wants from this program. We were funded as the inaugural cohort, and our project builds upon basic research and discovery to accelerate solution towards societal impact. And in our case, it is the development of a training platform at the end of next year. Hopefully we'll get there. So this is what I believe. A question that Laura had asked is, what are the challenges that we see? I believe that in order to realize each of our visions on how we contribute to future of work in whichever application space that we are working towards, such convergence efforts are not only beneficial in helping us see the problem from different perspectives, but also are critically needed. We cannot be siloed in our own domains to do research and say that it will benefit the future of work vision. These convergent efforts are needed that need to be use-inspired. That is, they capture our pursuit for fundamental discovery, right, for fundamental knowledge discovery, but are framed within a utilitarian framework on the application spaces that we have. So throughout our project, we constrained ourselves by saying, will emergency responders use this? Will they have access to such resources? So those are the challenges that we need to think of from the beginning as we do fundamental research, in my opinion. And that is the whole idea of what use-inspired research is. Now, of course, we lose some of the potential generalizability across disciplines, but in order for us to move the needle, to a point where emergency responders are safe, we really need to look at this occupational domain. So with Learner, we, very quickly, I want to talk about what we proposed to NSF. We want to develop a mixed reality cloud-based learning platform that can transform the future of work and workers in emergency response space by training the responders in the application of human augmentation technologies at work. So that is what we had proposed. And why we wanted to do this. If you follow Simon Sinek, I think he's a motivational speaker. He has this golden circle that he talks about, why Apple did really well compared to Sony when, iPods versus the MP3 players were coming out. And he talks about, we need to look at our core, which is why. And when we asked responders, what are some of your bigger challenges? The captain of a bomb squad unit told us that he is around 63, 64. We were sitting down with him and his peers, and he said, people look at us, just look at us, people look at us and don't want to join the force because of what we have done to our bodies. Right. So we have these veterans who are so passionate about being in public safety and serving the public. However, the chronic challenges and the chronic issues that they face deter newer talent to come into the workforce. And when we look at the statistics around, what the current workforce of emergency response looks like, we see a lot of skilled workers. So emergency responders don't really get trained, don't really have refresher trainings. They take a training and then 4 or 5 years later, they might take it again if they have the budget or not. And that's what happens here, in parts of US. I don't know, what, European emergency response training requirements look like. Recruitment and retention is a big issue. 20% of the workforce is injured. And then, of course, there are limited resources to train. How we want to approach this problem is by creating a platform that works on 4 tenets. The first tenet is making training either personalized or adaptive. So when we started thinking of what we want to do, we went for the moon, right? We went for the stars, which is saying that we want the training to be personalized to each individual. Within 4 months, we realized how difficult that is going to be for emergency response. Even though with emergency response, we have, one size fits all training right now. And it's important for the training to be adaptive because if you think of responders, they work in teams. And when you have teams that have varying levels of skills, that can hamper team dynamics and team coordination during an emergency. So what we want is we want to sort of create a level ground for all responders and so we can develop trainings that cater to specific learning needs, learning rates, learning preferences, as well as the type of work that someone is doing, depending on, how they are in the team. We also want this platform to be modular. We want it to be modular for various hats. It could be drones. It could be, ground robots. They could be augmented reality, like we showed earlier, or exoskeletons. The most important thing we wanted to make sure that the platform was accessible. This is the biggest issue with emergency response. They don't have the time or the budget for repeated training. And if we are able to provide, let's say, a curriculum to them that they can choose based on their resources and their preferences, we may be able to not impart all of the learning objectives of that curriculum, with 100% effectiveness, but at least they'll get something. So a fire department who doesn't have the money can utilize, a tablet or a phone to get, the knowledge rules aspect of a curriculum via a smartphone. And maybe they can say that I want to, utilize a different level with the VR headsets. So I'll talk a bit more about this later. And finally, we want the system to be scalable as well to other domains. What we really want to achieve is we want to make sure that our emergency response workforce is reskilled, upskilled, pre-skilled. We want to attract talent. We want to ensure that they are safe when they are, responding to emergencies, which will also help in the nation's, response preparedness. So we proposed a lot of deliverables in 2 years. So you can see over here, month 1 to month 17, this is what we wanted to tell them this is what we want to do. We want to develop use-inspired emergency response content in different training modalities that have various multimodal sensory cues. But as a first step, emergency responders can be in law enforcement, firefighters, and all of that. So we had to scope in. So we scoped in for EMS providers. We wanted to look at, what are the critical skills that EMS providers need. And so use-inspired VR content is created for them. We also are working with a system integrator to help in developing the cyber physical infrastructure for the learner system. How is the learner system going to be delivered? How is it going to be updated? How are people going to interact with it? We create adaptive learning algorithms so that it can, help responders learn and get to expertise development quicker. And then finally, we want to include 2 HAT modules, exoskeletons to augment physical capacity and augmented realities to improve situation awareness and team coordination. So this is how we want to measure learner at the end of our 2 years. This is what success means for the project for the first 2 years. First, during our first year and a half, in our labs, we want to keep testing, do several user studies for which I'll show you some results, where we want to have individuals interact with human augmentation technologies, see how they interact, see how they learn and adapt. And in doing so, we use physiological, neural, and behavioral metrics to sort of do fundamental work over here, relatively fundamental work, where we try to see, what's happening to, regions of the brain. Are they getting, strengthened as someone is going through a training in the lab? Are people responding differently based on some of the metrics that we collect? But what ultimately we want to do at the end of the 2-year project is evaluate a minimum viable prototype where the system is ready, right? A rough prototype is ready. And we want to take this to one of the training centers, TEAX, Texas A&M Engineering Extension Services. It's just in our backyard over here at A&M, is one of the largest training facilities in the world. They train about 200,000 responders every year, in addition to hundreds and thousands of workers from other occupational domains. And they really have like a big infrastructure where they have, outdoors and indoors infrastructure for simulating emergency. So in fact, we have rubble that came from 9/11. We have scenarios, train wreck scenario, mass casualty event scenario. So all of industrial fires like this. So this is a picture from TEAX. So all of this can be simulated. So we are working with TEAX in, getting the system to TEAX, having groups of people either trained with our system versus not trained with our systems on these human augmentation tech, and trying to figure out how they would actually respond in a high fidelity scenario that we would simulate based on the West fertilizer explosion event. And we would report technology acceptance and desirability outcomes. We would report efficiency of response and physiological metrics. So I am not doing this alone. What I wanted to emphasize over here is this requires a humongous effort from several experts in several domains. So I am a human systems person, so that's what my focus is. I'm the lead PI and I'm managing the entire project. I'm also focusing on adaptive learning, which is what I situate my research in over here. And then we have folks who help in innovation ecosystem, because sometime later down the lane, we want to achieve scale in emergency response. We have experts in VR development, we have experts in AR, we have experts in exoskeleton development. We also have industrial partners, so we can't do this in 2 years. Academic researchers cannot do research and then translate that into a workable product in 2 years. So we outsource or subcontract whatever we can. So we as academic researchers focus on the intellectual merit and fundamental discovery. We then provide system requirements to our industry partners. So for example, we have an industry partner called KBSI, who will actually develop the cyber physical system for us. We will tell them this is how it needs to be done, this is how adaptations need to happen, this is how this needs to be presented, and hopefully they'll do this and it'll get done. And then they work very quickly, so we are hoping that happens. We are also working with robotics companies to help us come up with prototypes of exoskeletons that are not available in the market just yet. And finally, the biggest thing is we are working with government agencies like National Institutes of Standards and Technology. One of their arms focuses on training for emergency responders. So they are part of our team and are guiding us to test and evaluate our systems in a way that would enable longer term standards acceptance as well as regulatory processes. So we are thinking about that really ahead of time. Apart from the folks that we work with, we also have an advisory board. These are our sounding boards. They are folks from emergency response organizations like the National Volunteer Fire Council, NFPA, National Fire Protection Agency. They are from the government, DHS, Department of Homeland Security, FEMA, and they are from industry, folks, from Ford, from Boeing, some standards like ASTM, American Standards, TM. I don't know what TM stands for. We just call it ASTM right now. And they are our sounding boards. We meet with them every month, and we as academics tell them, what about we do this? And they will call out on us if we have to. They will say, you're crazy, this will never fly. Or they will say, you know what, you're pushing the boundaries. So why don't you couch it this way so that it's a little bit more palatable, so that it can get rolled out relatively well. So this is really helping us ground our research. So we are not just shooting for the stars. They will even come back and tell us, are you crazy? You are asking to do something that even industry takes about 4 years to do. So, calm down, think of, incrementally moving forward. So it's been really helpful, hearing their feedback and getting advice on how we need to move forward. What we did before we actually started on our project was before the 2-year project, we had a 9-month phase 1 that was funded by NSF, where we established our board, where we did user-centered research. We called 50 emergency responders, technologists to TEEPs for 3 days. And we had them wear exoskeletons, we had them wear augmented reality headsets, we had them do a lot of different things. And based on their feedback, we were able to say that exos and AR are the 2 human augmentation technologies that they believe could transform future of ER work. So it was not something that we wanted, right? As academics sitting in our own bubble in our offices, never having to do any response. It was them. They wore the exos and told us, whoa, this feels different. I can see it being beneficial here, right? And so they carved out our scope. And with this phase 1, we decided to do 2 things for the next 2 years. We decided to develop EMS trainings for triage and patient handling. These are the 2 tasks that EMS responders do repeatedly. The way we envision the future for triage is that augmented reality will enhance triage during mass casualty incidents. And in doing so, our current scope is, how can we train first responders to effectively use augmented reality? And so that's what we wanted to work on. Similarly, for patient handling, our vision is that some patient handling techniques, the way we move patients or lift them, can benefit from exo use. And our current focus is, how can we train responders to not only use the exos, but also know when to use the exo and when not to use the exo. So some sort of operational decision-making capabilities need to be taught. So here is where we present our learner platform across multiple access levels that I talked about. So you can imagine access level 1 being training provided in low immersion, low fidelity, but is also low cost. So people can do this as often as they can. And then ranging to level 4, where it's high immersion, high fidelity, but more expensive. Typically trainings are done here right now. And that's why they are done like once in 5 years, if at all. So for triage, this is how we envision providing the same training curriculum across different access levels. In access level 1, we will provide training on triage using web-based contents and handheld AR. So we have already developed these systems, they are ready to go. In level 2, you can imagine, virtual reality headsets are relatively cheap right now. So a fire department can purchase several and keep in, and they can then utilize that, log into our learner, system, and use the VR as a training delivery mode. Third level is actually using the hat, which is AR, as a way to learn with AR. So it's a little bit confusing, but augmented reality headsets are more expensive currently. Hopefully in the future, they won't be as expensive. But now you can actually use AR headsets and modify your fire department facility, let's say the garage, into an emergency, disaster location. And level 4 is really, where you actually go to a training facility and get trained. Similarly, for patient handling, level 1 is web-based. So you basically train them, this is where exos are helpful. This is how you move with an exo, show them videos and whatnot. And access level 2, again, with virtual reality, you give them VR-based training. They really don't have exos at this point. So they are not really interacting with the physical exo, because currently even passive exos are about $3,000 to $5,000. So they are expensive. So in a firehouse, responders may not have it. But what we are training them is decision-making of when to use an exo versus not. But in order for us to do that, we actually need to do research to provide, the markers for how they make those decisions. In level 3, we are using exo emulator. This is where Sarcos Robotics is helping us, where an emulator like this with a VR headset can be situated in a training facility, and people can come and actually work with the exo emulator in virtual reality. So they can understand how an exo would reduce loads in their shoulder or may impose greater loads in their back. So this way now they get the force feedback. And finally, level 4 is actually working with an exo in the field. And then again, these two are more expensive than the first two, but are more immersive. So that's our vision for how we want learner to come in. So you can imagine a responder would say, you know what, I want to do, out of the 4 modules in patient handling, I want to do 2 in level 2 and then 2 in level 4, and they can choose to do so. And in this way, they have the flexibility to, get refresher trainings on aspects of the curriculum. My work over here is looking at adaptive learning. So what we want to do is, as people go through these trainings, right, we want to know if everyone has the same learning rates, they have the same preferences, and how can we adapt the learning for not only deficiency-based training, which is if they're struggling, you give them some cues and help them as they are learning, but also proficiency-based training, which is what emergency responders really need. They want to short circuit expertise development. These are exact words that they have told us. Can we short circuit expertise development? Because we don't have the time, right? And so what we want to do is use sort of like an adaptive training framework to make things more challenging so that hopefully they are able to learn and sort of see where there are gains in training that we can identify. I won't go into the detail of this, but I'll highlight 2 things over here. One is that in order for us to develop an adaptive learning framework, we can't really look at, let's say, the rehabilitation space where they do a lot of adaptive learning, because responders may not respond a certain way. One of the things that we are trying to do right now is follow the instructors. We follow the instructors at peaks. We see how they teach in person. We ask them questions on, what sort of cues are you looking from your users, and we sort of note down the explanations they give to various concepts and theories with examples from when they actually responded to an emergency. I had my entire team go and take triage and patient handling courses multiple times as participants, so they can understand what the course is about, but also how a user goes through the course at different levels of learning. So that's one level of human-centered learning that we are trying to understand. The second thing is adaptations will be limited to our access level. So for adaptations to be utilized, we need to get information from the user in real time, right? So, and information could be things like they're not understanding. So they might be frowning, like they are, when I'm teaching someone and I see someone, frown, I'm like, okay, so this person is struggling. How do we get that information from the user? Because in access level 1, they are holding a phone, right? So we can't get eye tracking data. We can't get brain imaging data. We may get some movement data, but would that be useful? We don't know. So for each access level, the markers that we can get are also different. And that's what we are trying to work on. We're trying to see with access level 1, with clicks and interactions on the computer screen, can we do similar level of adaptation as we would if someone is in a VR headset and we can get eye tracking data? So that's where the intellectual merit comes in. Although that's also where some of our challenges as researchers come in. So very quickly, I want to talk about 4 studies that we had to very quickly do within a year. And this is just within my lab. the other researchers had to do similar studies in their lab. This is why it's called the Convergence Accelerator, because we had to accelerate our research and development within the 2 years. So the first thing I'll talk about is we wanted to know whether with virtual reality training under different states, stress versus no stress, how learning is different. We know that from motor learning studies or from psychology studies that stress impacts learning. We wanted to see whether we could use different markers to replicate that in VR and ensure that we can use that as an adaptive model. So we called firefighters in the lab, we made them go through different trainings, and we collected brain data and we collected eye tracking data. We used machine learning models to simulate whether we can, classify them being in stress versus no stress in the learning and in the evaluation stage. And we found that brain data was really, we found that with 80% accuracy, which is the best we can do right now, we found that we could classify, whether someone was stressed or not during training or during recovery, and that can enable state-based adaptations. We found that with brain data that our machine learning models were robust and were giving us very similar results. That is 80%, depending on the environmental conditions, around 80% is the accuracy that we get. With eye tracking data, which is more accessible, right, compared to brain data, we found that general accuracy was around 84%. However, when we changed the environment, sometimes it reduced to 60%, which is as good as chance, right? So that's not really, classification at its best. So this is where we come as researchers. While eye tracking would be really good and easy to do in the field, brain data is more robust. How do my team reconcile? We are still trying to figure out, like, how do we reconcile? We know we cannot collect brain data from the field. So what do we need to do next in order for the two roads to converge? If you have any answers to that, I would happily take that. But right now, that's where we are on this sub-project. On another project, we for the same learner project, we had people come in on 4 different days and train them on drone navigation over the course of 4 days. So we basically took a NIST drone training program that happens in physical world and converted that into the virtual world. And we had people do, different modules. So they had waypoint navigation, precision demand, obstacle avoidance, and external perturbation. So skills are improving over time. And we collected eye tracking data and brain data. Here we are using just performance data because we wanted to see if only performance data can help us in doing adaptations. So here is an example of our adaptive model. So someone who did obstacle avoidance, we get their data in real time. So this is their data in real time as they're flying the drone, right? So their position data, how smoothly they are controlling the drone. So the drone control is physical, using an actual physical controller, but they are seeing the response in VR. So we are doing sensory motor training over here. So based on the performance data over here, the adaptive model told us that they would do well with external perturbation. And they actually did relatively well with external perturbation. So external perturbation was they had to make a figure of 8 across different planes. And in between, there was a bird flying or something, some perturbation happened and they had to deal with it. And they did really well. But for someone who didn't do obstacle avoidance well, our model told us that they would fail at the external perturbation. So what we did is we had them, so you can see over here, they couldn't really control the drone well. So for them, our adaptation was visual guidance, was telling them, there will be an obstacle over here, so they can pre-plan, they can have preparatory actions planned. And so they did relatively okay over several adaptation trials. And then where is it going? And then their external perturbation was good. It wasn't the best, but it was definitely not bad as our models had, warned us. So this is an example of how adaptation could happen with just performance data. So we were very happy with this because performance data can be done with access level 1. And so we were really happy with that. I'm going to skip through 2 others because I think we are out of time over here, but we have also done 2 studies. One, adaptations with passive exos. Here we are looking at how people learn how to use an exo over the course of 3 different days. And you can see over here, we are collecting eye tracking data, EMG data, brain data as they're going through a trail making test that we were very proud of converting from a digital or a paper pencil to to an actual physical infrastructure. And we had the same level of robustness for trail making. And then we looked at the brain data that, exo group over days showed, activation over time, that the control group showed automaticity. And we found that the performance was much better in the control group than the exo group over time. So how do we adapt for the exo group to get to this point and better performance is something that we are working on right now. And the other thing that we are working on is the tasks were very structured, right? But emergency responders are going to be lifting patients. And that is a whole another set of problems. But in order for us to get to this point, we had to do the basic research first in a very accelerated way. So we are still analyzing data from this very dynamic task and this 200-pound dummy that we got from the training facility. Finally, we are also looking at augmented reality, interaction learning. We are doing multiple things. We are comparing how emergency responders interact in a physical triage tag versus a virtual triage tag that our collaborator has developed. And we are also trying to utilize how people learn how to use AR interactions and how those AR interactions can help us in identifying if someone would do poorly in using the virtual triage tag. So this is an example of someone training in just pure AR interactions. This has nothing to do with any sort of emergency response operation. So you can see they're using different AR features to train, and we have them do this multiple times. We are developing adaptive algorithms that can help them get to efficiencies sooner. And once they do that, we test them on an actual triage, virtual triage tag task. So this is how a responder would actually see a triage tag when they are responding to an emergency. So they need to learn these interactions, right? So we are trying to test them on this. So our evaluation would be using this exact interaction, but in the field, outside in the field, and seeing how emergency responders interact with this virtual triage tag. And will that help in improving response efficiency? So with that, I want to close with challenges and hindsight, right? So what are some of the challenges, and why hindsight is 2020, and why we couldn't proactively say that these will be challenges. The first is there is a difference in quantifying learning on the hats, which is how an exo moves and how your body moves with an exo, to learning on the ER work process, which is using the exo during patient handling. And it's very difficult to parse those out in terms of time for research. It'll take a long time to get to integrating these two, but we have to try to do this within 2 years. So what we have to do is let go of some or figure out innovative ways in which we can sort of assess both of these and see how we can integrate them. There is no right answer. The other challenge that we have is there are fundamental knowledge gaps on how different learning modalities, right, like XR, MR, can impact learning across different people, right? So we talk about using VR as an educational tool. That's great, but have we evaluated where are the learning gains and losses when we do it physically versus in a virtual environment? Like, are we leaving someone behind because they can't really interact that well in a VR environment? And there are these fundamental gaps. And this becomes even more relevant during the pandemic because, with the pandemic, we had to go remote. Workforce trainings have declined. In-person workforce trainings that require, embodied cognition have declined in the past 2 years, and people are going more virtual. So are we losing critical skills that need to be done? Are we creating gaps in developing critical skills that can only be gained through these physical interactions? And so we need to have a better understanding of what are we gaining, what are we losing. And that documentation requires fundamental research. The next is system integration. Like I said, I cannot even imagine if someone goes on a computer screen, logs into the learner platform, then that system says, wear on your AR headset. And then they wear the AR headset. And now my adaptive algorithm needs to work with the AR headset, also with the cloud-based platform. I can't do it. So system integration is a big issue. And so if you are planning to embark upon a future of work project and sort of this is your vision, then be open to delegating some of the work that is not in our expertise area to something else. I think more often than not, academics want to do it all. And what we learned over the past 2 years is it's important to let go. Finally, how do we measure impact of the project? Will this really move the needle? We know we'll be doing an evaluation at the end of 2 years and we'll have some metrics to show. But what happens really after that? So it's really important to embed responders in our workflow at all points. That's why we meet with our advisory board every month. And they'll tell us if something won't work in the future. But it's very difficult to evaluate for the future right now. And finally, I can't emphasize enough on team science. This project required a lot of different people to work together. So you can imagine everyone, different personalities, different professional goals. There is someone who may have a goal of directing their vision, but the burden is placed on another person. This person is really happy in doing whatever they want to do, but they can't see some of the blind spots that have been created. So team science was something that I had to learn very quickly on how to manage this large group of people with their own expertise and their own ideas and their own, vision for where this needs to go. So I have more on the project over here. You can go and learn more. But with that, I'm happy to take any questions right now.